Alan Ager is going to speak next. He's an operations research analyst with WETEC, which I always get wrong. It's the Wildland Environmental Threat Assessment Center? That sounds so scary, doesn't it? I don't know. He's going to be talking about application of the landscape treatment designer for prioritizing restoration and fuel management projects. So this is getting on the east side and thinking big landscapes, think accelerated restoration as one of the tools, as this being one of the tools that'll play into that, I would assume.
Could be.
Could be. Okay. Help me welcome Alan, please, everybody.
How's this work going?
Pointer.
Okay.
And up and down.
Okay. Okay, thanks, Cheryl. So I have 26 slides and what, 25 minutes? So I'm going to move along at a pretty good clip, and then hopefully we'll have time for questions. So I'm going to talk about the landscape treatment designer, optimization tool for restoration and field treatment planning. I want to start by talking briefly about optimization and forest planning. It's a long history of research in this area for fuels, wildfire, to arrange treatments to block fire, maximizing timber production, and dealing with adjacency constraints. Wildlife people have done a lot of optimization to maximize connectivity. There's a huge literature on it. Been around for a long time. This has been around longer than the term landscape and the science of landscape ecology. So some of the tools, there's hard optimization tools, mathematical programming they call it, soft optimization, heuristics, pseudo-optimization, which are sort of shortcut methods. And the primary application these days is industrial forestry, and historically was in federal planning. We used it for plan and other linear programming techniques, a form of hard optimization in the 80s and 90s, but it was largely disappeared from the scene, and so you could call this kind of a resurrection. So I put together this landscape treatment designer program for a couple of different reasons. One is that we spend a lot of effort on assessments, and we don't have simple decision support systems to sort of consume these assessments and expose investment choices and trade-offs. And nor do systems exist to explore optimal mixes of investment strategies, sort of the frontiers of restoration. By investment strategies, I could mean anything related to aquatics, botanical resources, wildlife, biodiversity, whatever indicators of the day or of interest. And choices exist between alternative strategies and investments on different parts of the landscape because of all the landscape heterogeneity in relation to our management goals and our constraints. And I know that's evident to everybody, but we don't often think of the problem in that context. So Gifford Pinchot, when he said the greatest good for the greatest number, he really meant optimize the greatest good for the greatest numbers, where I'm coming from, all right? So now, another reason for this program is we need better tools for landscape field treatment design, and I work a lot on east side forests throughout the West. And we kind of have this framework for field treatment planning that involves putting together, doing wildfire simulations to calculate risk factors, which are the likelihood of fire and the intensity of fires in spatially explicit locations. We do, quote, burn probability modeling over the entire United States. There are optimization concepts about impeding the flow of fire through landscapes that we need to bring into the picture. There's wildfire ecology, whether we're trying to bring fire into the landscape or trying to use natural barriers to stop it. And then we have different spatial patterns of values. You know, in some places we have defined wild and urban interfaces where we're trying to block the flow of fire to wild and urban interfaces. In other cases, we have dispersed spatial patterns of values where we might have recreation sites or owl nest sites, and we're trying to protect little fiefdoms all around the landscape. So there's all these different spatial patterns of values, and all these come together to create what might be considered some optimum spatial fuel treatment strategy. So on this spectrum of fuel treatment goals, from restoration to protection to containing fire, we have, for instance, this is kind of my taxonomy of fuel treatment strategies. We have something called low hazard fire containers, which is what a lot of people are doing on east side forests throughout the West, and that is finding areas where we, for instance, have old growth dry forests that have stands that have undergone densification, and we want to go in and lower the fire hazard, so when fire does come, we don't lose the ecological values of the dry forest, and moreover, it makes it easier to manage prescribed fire within which. So we treat to get rid of the high hazard stands within, and we treat efficiently so that we're left with the largest container to manage fire. Okay, so moving along towards protection, if we have some kind of vegetation that form natural fire breaks historically, we might restore those. Like, for instance, aspen stands in the Rocky Mountains were natural fire breaks, but they're being encroached by conifers. And so we go in and thin them out and restore their landscape functionality as natural fuel breaks. This is an entirely different spatial pattern of treatments. We have focused defensible fuel breaks where we might have a WUI shown in orange, and we have, we'll put fuel treatments around the WUI to stop fire from entering it and facilitate suppression. I'll skip dispersed fuel. Well, dispersed fuel breaks might be around campgrounds, wreck sites, owl nest sites. Treatment optimization model that Mark Finney developed puts treatments out in a spatially optimal way to stop the flow of fire from one end of the landscape to the other. So buying time so weather and suppression can put it out. And then at the extreme, we might have high hazard fire containers where people are treating along roads and treating stands prone to crown fire along roads and ridge tops to build a network so that fires can burn within each of these things. And perhaps we lose something, but they can be stopped. And there are people doing all of these. I didn't make these up. I've observed all of them. And I wanted a way to model them to test their relative efficiency under different scenarios. And that was another reason we built this program. So because doing this in GIS is complicated and takes a lot of time, and of course the first thing you do in a GIS exercise is do it over because you made a mistake. So LTD overview, briefly, modeling a spatial planning problem in this program and in general involves three key things. One, an objective function. So it quantifies the potential response for management activities, whether you're doing stream restoration, whether you're doing wildlife habitat improvement, or whatever you want to quantify. If I do some management to a particular area, I get this back. Could be thinning volume. All right, constraints. We all have constraints, specify the restrictions on budgets or activities, acres, dollars, people, whatever. And management thresholds. Under which conditions am I going to go in and apply management, whether it's, restoration, passive, active, whatever. But what are my management thresholds? Okay, so three things that you need to frame this problem. And this program, which operates in polygons, will maximize or minimize this objective function subject to constraints. This is a classic operations research optimization problem. Management is allocated based on the treatment threshold, and then there's several options. You can aggregate where the management units need to be connected. You can iterate, so you can repeat the optimization to essentially lay out projects on a landscape, and you can step your treatments and constraints and do sensitivity analysis. Aggregation, we aggregate because we build project areas. I mean, that's what this workshop is about, where do projects come from, okay? So we're aggregating, so this program has to build a container that is connected by a condition specified by your management threshold, all right? So hardware and data requirements, there is actually a 32-bit version, but the latest is 64-bit. Size of the hardware depends on the size of the problem. We use shapefiles of management units that can be stands, can be HUC 4, 5, 6, could be ranger districts, and attributes that describe objectives, constraints, treatment thresholds, the availability of land for management, and also some information about the spatial location. So this program started out quite simple, but it isn't anymore. But so, so here's the interface. You can download this. You load a shapefile, and then you get a shapefile output. And so you specify an objective function. This one is cubic foot thin removal volume, and a weight, and a type that you get it when you treat. Your treatment thresholds, I'm running, actually this is a more complicated scenario that I shouldn't have shown here, but I'm running the removal cubic feet thinning volume in the stand must be at least 500 up to 4,000, and I'm stepping at 500 per run. I'm maximizing it, I'm iterating, and I'm repeating it for the sensitivity analysis, but there are several options, and I'll show those. And my constraints are a project size where I can treat up from 200 hectares up to 3,000 hectares, and I'm stepping 100 hectares. So I'm going to look at a whole range of optimization. So I'm probing this landscape for spatial optima for these conditions, meaning a thinning volume. I'm optimizing the thinning volume. There has to be contagion to the project. Okay, so this is sort of like the Weyerhaeuser option. All right, so and the outputs. Shapefile with management priorities, i.e. projects that maximize the objective function given the constraints. So, here's an example. Typically the project areas are kind of circular, but we're sort of fixing that to fit them into the landscape better, but they're not always circular. And so these are different projects labeled with their priority based on the objectives. And then with sensitivity analysis, you get outputs that show as you change management thresholds and change constraints in terms of how many acres you can treat or whatever per project, shows you what you get back out and kind of where the optima exists and where things fall apart, okay, which we'll look at in more detail. I don't really have time to explain the search algorithms, but it's very simple neighborhood search where it just sort of collects stuff together, but they have to be aggregated. So example, Mount Emily Wooey in the LeGrand Ranger District. This is a very simple example where this is the density of residential structures is coded. So high density of residential structures is red and lower is yellow, and we're gonna optimize the home density, and we have to treat every stand that has a flame length greater than 1 meter, and you can treat between 500 and 700 hectares per project. And we've divided the area up into priority projects now. Red is the highest priority, followed by probably this one and then that one, and on and on. And the black areas are the stands you have to treat based on the treatment threshold that you put in there. And if you don't like it, you can change it and rerun it in about 5 seconds and get another. This is an example that's in the GTR, and it's for the Ochco National Forest. And they told me they wanted to treat areas with high concentration of overstocked stands, large trees and high fuel hazard. Of course, they can't cut anything over 21 inches, but they did need to generate some revenue from their projects. And so they gave me a scoring system for every stand based on stocking, based on structure size class, and based on fuel hazard. Just 1 and 2 for this, 1 and 2 for this, and 1 and 3. And these scoring systems are quite frequently used on national forests. I mean, you probably all have done this or seen one of these before. And they said, find the optimal project areas based on that. And so we are out of sequence. Oh, no, so, okay, so here's the setup. I put the 3 indicators as the objective function. I said you had to treat if the flame length was more than 2 meters, modeled flame length, and you could treat between 8,000 and 9,000 hectares, quite large areas to treat. And I enabled iteration to repeat until we had treated the whole forest or built projects in the whole forest, and I said maximize the objective function. And so this was a project priority list. Red is high. These are the priority numbers from 1 to 16. So it divided the forest up into different priority areas based on those objectives. And some of their polygons are sort of stringy, and that's why you get some of these weird effects. And you can't fit projects in everywhere. This isn't, exactly go here and delineate your project. This is, this part of the landscape is where to look, is the idea. Another case study on the Wallowa-Whitman, they said they wanted to create high hazard fire containers surrounded by defensible zones. They wanted to treat along roads and ridges near wildland urban interface and treat stands with crown fire behavior. So the input data was distance to road, distance to WUI, slope position, and percent stand in crown fire condition. And the idea was to create this high hazard fire container picture that I showed earlier. So these are treatments along the road network, for instance. And so I ran that, and using those values in the objective function that prioritize the ranger district, and these different colors, these are the stands that needed treatment. I haven't outlined the projects, but you can sort of get the picture of all the different project areas. And red was high and green was, I used just random colors on this. But when you zoomed in, you can see sort of these networks of stands that were close to roads and on ridge tops that sort of resembled that. And it was sort of a quick and dirty test of building in some topographic stuff into the picture. Then I did an optimizing dry forest restoration, and I'm going to skip over that, but it just came out in Ecosphere. It's a long paper that where I used treatments to maximize the protection of old growth ponderosa pine in contagious areas so that they could maximize the restoration of natural fire, essentially. Build low hazard fire containers and protect ponderosa pine from fire. And it's described in excruciating detail in that paper. Then one day I decided the Region 6 was doing their TRAX terrestrial ecology assessment, and they published it, and we of course have our watershed condition framework too for the whole nation, and these are HUC 6 level outputs, and I thought, well, I'd build it into sort of large areas and prioritize the whole region. So I put in the 3 scores, priority species, the TNCCOA, and I forgot what that is, the watershed score, and then I also put in a hazard metric that I'd calculated for each HUC 6 watershed, and I equally weighted them, and I said that you could treat between 100 and 200,000 acres. Treatment by, this just means that if the watershed score was greater than 1, you had to treat it. So it was just sort of an arbitrary treatment threshold, and ran it at the HUC 6 level, and it prioritized, and I'm just showing this for demonstration. I'm not suggesting any priorities here, but this, each color is a block that received a specific priority in the process. So in this case, I'm using HUC 6 stands and doing it at a very large scale. Okay, and then the Blue Mountain study, which is the last one. And so when this whole idea of accelerated restoration surfaced and papers started materializing, for instance, National Forest Health Restoration and Economic Assessment or Restoration on Oregon's Eastside Forests, led me to think about questions about how projects should be fit into this landscape and what's an efficient approach to restoration over the 4 Blue Mountain National Forests. Specifically, what are the management trade-offs between restoration, wildfire risk, and economic benefit, and what are the optimal design parameters? For instance, area treated, treatment threshold, percent of project area treated. Do we have spatial optima, and what's the effect of conservation and WUI protection on these optima? So if you think about what reduction in wildfire risk, which is sort of the driver, one of the drivers of this whole accelerated effort, and restoration, which is another, and economic value, because in the east side we're trying to keep these mills open, and it's a major part of the equation, that as you vary these parameters, you might find local optima where you can achieve all of these at once in specific places. And given the landscape heterogeneity over there, it makes sense that you could. So just a couple outputs, and these are just some really early runs. There's 200,000 polygons on the stands of all 4 forests combined, and we run those and through some various scenarios, and we've just started doing that. But this is the effective fire risk threshold and treatment area and volume thinned per project. So as you contemplate projects that are, say, 500 or 1,000 or 2,500 hectares in size as your treatment constraint, how much you can treat, and then you have a treatment threshold where, well, I can treat anything below a 1.5 the fire risk threshold, high values mean high risk, low values is low risk. So if you're only chasing high risk stands, meaning 9 or above, you don't generate any thin volume because high risk areas don't have any, and probably because they're right close to WUIs and other facilities and infrastructure. The risk data came from the West-wide risk assessment. It's sort of an early release of the data, but that's their definition of risk. If you relax your constraint on chasing wildfire risk, as your project size increases, the total thin volume per project dramatically grows along with it. And then you can see it sort of ramp down as you tighten down on chasing fire risk. The efficiencies of generating thin volume are reduced dramatically. All right, so makes sense. We don't see sort of any local peaks or optima, but we've just started this, and I expect to find something before we're done, including errors in the way we did that. But and this is the effective treatment area on thinning threshold, treating ecological departure. So we took ecological departure index from land fire, which goes from 0 to 100, and we just we summed it up in the project area. If it was treated, it's summed up, meaning you're dealing with the departure issue on a particular stand. It's a pretty simple way of looking at it. But as thinning volume threshold is increased, meaning the minimum thin volume that you acquire from the stand, the amount of departure you deal with goes down, although it goes down very gently if the project areas are small. So what's going on here is we're able to find niches in the landscape where we can continue to deal with departure, chasing more and more thinning volume out. But as the project areas get larger, it's harder to squeeze them in the landscape, and that's because of the spatial grain of both the volume and the departure, and it makes sense. And then you fall off the cliff when you get out trying to find stands with over 2,000 cubic feet of volume to build a project area. So that's some kinds of things we're going to look at. And this is a map of optimized project areas, but I'm not going to specify what I optimized for. Consider it either morels or pod plantations, but because people start freaking out when you put priority maps with this east side restoration stuff. But that's the kind of stuff you get out. And this is just, I think 10. So you can tell the program, just give me the 10 best optima or give all the optima. And of course it takes a long time. If you got 100 optima, it can run for a while. So, all right, so, and then this is one more, how big should projects be? And it's kind of interesting. So, you know, we're talking about bigger and bigger projects, and yeah, that makes sense from a NEPA standpoint, but what about the project size relative to the grain of what we need to do, which is restoring fire or restoring structure or whatever? And so as the thinning threshold is increased, meaning the minimum thin volume that has to be obtained to treat a stand is increased, and then the treatment area is increased, you get all these different trajectories. And when you get in a spot like this at 1,500 cubic feet of thinning volume threshold, the decision about the project area makes a huge difference in what size, about the treatment area, how much you treat in the project has a huge bearing on how big the project gets, okay? So this is so in other words, it's hard to see with all the colors, but say for instance, if you have the capital or administrative capacity to treat 700 hectares, you're on a line in here. If your thinning volume is minimum thinning volume is 1,500 cubic feet per stand, that is going to generate a 50,000 hectare project, and you can't achieve it with less. I'm just kind of pointing to a spot on there, but that's what this graph does. The variability in the vertical dimension shows the local spatial optima, the phenomenon, and it shows the sort of system thresholds right here in this whole problem of how big should a project be. So we'll dissect this more and try and understand it. And so this program can be downloaded at arcfuels.org/LTD, and there's a tutorial and a GTR case study. So, all right, and I don't have time for questions.
Questions? questions for Alan? No? There must be some. Cindy?
So your managers are giving you their priorities, and you're translating that as ways to put into the model. What kind of feedback would you give them on how to set their priorities in a meaningful way? I mean, you must have run several of these. What would you do? What kind of priorities would you?
Repeat the question.
What kind of priorities would I give the managers after running this? So, well, I gave 4 case studies, so the recommendations would be different for every case study. So are you referring, like, for instance, the recommendations on the first 3 case studies were really, where should they go? Where should they be going, and what is the cost of them not going there? I mean, right now, we take, like one of those game board dials and flick it to figure out where the next project is, in my opinion. And I know there's considerable thought that goes into it, but sometimes, that's what it appears. And so there are sort of people higher up in the agency that wonder about this stuff. This is a way of validating where you're going and explaining the cost of going where you did go if you didn't go there. So it's a trade-off analysis, and we don't do that in the Forest Service, and we should be. So my recommendations to managers are to look at outputs from a program like this to understand what they're trading off in their current decision space. In terms of the east side restoration, we've just scratched the surface in mining that data. We don't understand it spatially yet. It's 6 million acres, and there's hundreds of Huck 6 watersheds and stuff going on that I don't think we know. But when we're done, we're going to be able to understand what the trade-offs the Forest Service made when they decided to start investing their restoration dollars in a particular place.
Wouldn't that argue that you should be using the same criteria across the larger landscape in order to compare those?
Well, 6 million acres, that's pretty large.
Yeah, but you're changing your criteria in all of your different cases.
No, we're taking the landscape and doing sensitivity analysis to understand if we changed our decision by 10%, what would it do? If we went from how big should a project be? I mean, why don't we all shout out a number? And I'm telling you that we don't analyze how big they should be from a restoration efficiency standpoint. And since dollars are limited, and we have attainment to do, and we have a backlog of fire restoration to do, that we ought to be looking at more efficient ways of doing it. And this is a way of understanding the scale, the efficiencies of different scale. In economics, you learned about the guns and butter curve, where, you can either produce guns or butter as a society. And in our case, it's possible that we can only, what is the relationship between fire risk and thinning volume to save mills, or between aquatic habitat and thinning volume, or fire risk and aquatic habitat? We don't know any of those. I mean, I challenge anybody to show me a graph on a real landscape that has quantified those trade-offs.
Thank you, Alan, very much.
All right, thanks.
Let me thank Alan, everybody. When I first met Alan, he was working on the Mount Hood National Forest, and he literally had like 6 CPUs all lined up, connected together, and was running programs that would take like 10 days to crank out an answer at the end. Yeah. Oh, excuse me, it was only 5 CPUs that were linked to it.